Hi and welcome to our video. We are Group NFMY 2, and in this video, we will show you on our product, the Rolling Element Bearing Tribometer. This tribometer is specifically designed for testing the performance of thrust bearings. There are 5 of us working together in this project: Khaw, Rifhani, Harrith, and Aina. Before starting, did you know? Thrust bearing failure from friction causes major machine downtime. But commercial tribometers cost over $5,000. Our design is over 95% cheaper. So, what problem are we solving here? Well, commercial tribometers, especially those that can measure frictional torque in bearings, are really expensive. Prices can go from $5,000 all the way up to $100,000, which makes them unaffordable for most universities, students, and small research labs. Without access to this kind of equipment, it's hard for engineers and students to test things like friction, wear, or lubrication, which are super important in real-world mechanical systems. Even here in USM, we only have a pin-on-disc tribometer and a 4-ball tester, and neither of them can test thrust-bearing friction torque. That's where our idea comes in, and it connects directly to SDG 9, Industry, Innovation, and Infrastructure. Our goal is to make tribological testing more accessible and affordable. This tribometer supports Sustainable Development Goal 9 by providing an innovative, low-cost experimental platform that strengthens engineering research, laboratory infrastructure, and product development. So here's our solution, a low-cost lab-scale tribometer. Showing here is the tribometer version 1 that we built last semester. We designed and built it using affordable materials and simple electronics. It can measure frictional resistance and torque during thrust-bearing operation. It's perfect for hands-on learning, material testing, and even small-scale industrial use, whether in student projects or research labs. Showing here is the core components and specifications, including a DC motor that can speed up to 425 revolutions per minute, a torque load cell that can detect up to 1000 N load and 10 Nm torque, a linear actuator which can apply axial load up to 700 N, a bearing cup, and a thrust bearing. However, some issues remain problems. First problem, inconsistent applied load by the linear actuator throughout the testing. Second problem, complicated bearing changing mechanism. Thirdly, improper speed control and measurement. Next, lack of temperature monitoring system. Lastly, misalignment and setup instability. Showing here is the control system of the thrust-bearing tribometer. To begin, turn on the main power switch to activate the tribometer system. Once powered on, the control system and sensors will initialize and be ready for operation. Next, press the load button to tare and calibrate the load sensor. This step ensures that the load sensor reads 0 before any external force is applied, improving the accuracy of the applied load measurement during the experiment. After calibration, use the hydraulic jack to apply the desired axial load to the thrust bearing. The applied load can be adjusted gradually while referring to the real-time load measurement displayed on the control system, allowing precise control of the test load. Once the desired load has been applied and stabilized, press the torque button to tare and calibrate the torque sensor. This removes any initial offset and ensures that the measured torque corresponds only to the frictional torque generated during bearing operation. Then, press the motor button to activate the motor. The motor will rotate at the preset rotational speed, with closed-loop RPM control provided by a magnetic encoder, ensuring stable and accurate speed throughout the test. During operation, all parameters are measured and recorded in real time, including applied load, rotational speed, friction torque, and temperature. These data are used for further analysis of bearing frictional behavior and performance. A thrust-bearing 51100 is tested continuously with 3 trials. For this semester focus, which is the feedback control system, we have made a great success on the feedback control system using the magnetic encoder to allow feedback control the motor speed. Other than that, the results seem consistent by comparing all 3 trials. That's all for this project video. Don't forget to like and share our video. Thank you for your attention.